Okay. Sí, muy bien. Entonces, yeah. Welcome everyone to the weekly colloquium of the Physics Institute of the UNAM in Cuernavaca, in Mexico. Yeah, this colloquium takes place within the conference on random matrix theory and its applications, which we celebrate this week in honor of the birthdays of Thomas Seligman, François Lever, and Jacques Bachot. And our guest today is Tomaž Prosen from the University in Ljubljana in Slovenia. And so thank you very much, Tomaž, for coming to Mexico, for visiting us. I think the last time you have been here, it was only virtually over Zoom. So I'm very happy to meet you finally in person. And yeah, we're looking forward to your talk.
Yeah, thank you, Thomas. Yeah, so it's really a pleasure to be back in Cuernavaca after many years. I was calculating the last time I was here was probably 2011. And the first time I was here was 99, so 25 years ago. So it's really a pleasure to be back. Thank you for invitation, Thomas. Yeah, it was a pleasure. And also to give the colloquium in this nice institute. So I will speak about, as you see, I have put rather a generic title. I will speak about quantum many-body chaos, which has become recently quite a topical field of research. I'll give you my take on quantum many-body chaos and some results that we have been in our group responsible for. But I'll try to, this is a colloquium talk, so I'll try to be as little technical as possible and try to discuss the main questions, the main puzzles, the main concepts, open questions in particular, and so on. So, okay, so this is just a flash through several of topics that we are working on in our group. I will not discuss any other of those except for the one with bold here. But if you are curious about anything you want to discuss, you can discuss anything else. But so so what is about? What is quantum chaos about? That's or many-body quantum chaos, right? So, I also apologize to those who have heard some version of this talk before, because I gave this talk maybe more than 10 times in various, well, not this talk, but the versions of this talk. And this is maybe the last upgrade, but still. And in one of the last upgrades, I left out the word exactly solvable models of quantum many-body chaos. So, but you should still know that I will stress most the exactly solvable aspects. So I will look for models which you can solve exactly and which you can teach students, let's say, So the model like this. So I'll go back to basically elementary course on dynamical systems and chaos theory, and what you teach in the first kind of lectures, in the first few lectures of dynamical systems or chaos course, is models like this. So this is a cat map, a famous Arnold's cat map. And this gives you a main mechanism of chaos, right? This is the so-called dynamical mixing. So the way that chaotic dynamics relaxes so that it mixes, it provides uniformity of densities in phase space, right? You start with something non-uniform, like a picture of a cat, and then after a few iterates of this simple map, you get something. This is just one iterate, but if you repeat it, most of you or all of you have seen this figure, so I haven't put them here. But this model, besides being simple and having the main kind of ingredient of chaos, is also exactly solvable. So you can compute correlation functions analytically, for example. You can compute Lyapunov exponent analytically because it's just an inverted harmonic oscillator in compactified phase space. So we want models like this in quantum many-body physics. I was really missing this kind of concepts in many-body physics for many years. And finally, I think we came across a couple of families of models for which one can do some calculations explicitly, or even prove some statements about spectral statistics. So as you see, I will go along and discuss these things. Okay. So now just to give you further motivation, of course, life is not as simple as cat map, right? you have many different kind of universality classes of classical chaos, if you want. You can have cat or its perturbed version. And if you perturb the cat, you see, I mean, this is what happens to phase space, right? This is 3 iterates, 5 iterates, 7 iterates. Then everything is kind of gray color because it's uniformly mixed. This is a phase space, right? Q and P, 1 degree of freedom, 2 dimensions. Nothing very interesting and nothing very different from the unperturbed cat. So I also want to stress that perturbing chaotic systems is something very interesting, and it's something very different than perturbing integrable systems. And I come back to that at the end of my talk. But I want you to keep this in mind. I mean, because we are always wondering, I mean, how to treat generic systems, right? And we are always thinking, okay, let's start from the free model, a Gaussian theory. You perturb it, and then you see that perturbation theory is full of divergences, and everything is kind of ill-defined. The infinities fly around, and so on. So what I want to do now is, I mean, what I do at the end of my talk, what I try to propose at the end of the talk is just to turn things around and to perturb around chaotic theory. And that's what mathematicians did many years ago in the 70s. They speak about structural stability of chaotic dynamics, of hyperbolic flows, for example. This is an example, right? So this is a kind of paradigmatic example of structural stability. You take a cat, you perturb it a little bit, the topology of phase space stays the same. So it just gets curved, but nothing really new appears here, right? But then you go to a different model, like a standard map. I mean, still, for most of you, these concepts are well known, but even if they are not, I will not define them because I will try to reduce the amount of formulas to a minimum. But these are different, qualitatively different types of dynamics. This type of dynamics has mixed phase space, so they have some little island somewhere. I mean, this is a sufficiently strong chaos parameter so that regular parts of phase space are very tiny, but still, topology of dynamics is very different. So you see, this is generic kind of Hamiltonian dynamics. Then you have integrable maps, integrable systems, right? They don't really mix. And then you have some strange maps, which we have proposed with Giulio Casati many years ago, which we put a name triangle map, which have a very different mechanism of mixing. So this is something that, again, I would be happy to talk to anyone interested. Actually, we started working on that in Cuernavaca 25 years ago. So that's something that I would like to stress here, right? I mean, these triangle maps or triangular billiards, this is something that came out of studying triangular billiards as an abstract version of triangular billiard bounce map. And it has this phase space flow, which is very, very different from any of hyperbolic flows. Still, it provides mechanism of mixing. And we discussed that with mathematicians like Bunimovic for many years. Nothing came out of this because it seems that hyperbolic ergodic theory just doesn't have the tools to treat this type of simple dynamics. Okay, but that's just a sidetrack. So then, okay, I mean, you have seen models that people liked in this business. These are billiards, right? I mean, yeah, these are, you know, quantum billiards, right? These are wave functions of quantum billiards. Then people discuss spectra of quantum billiards. Yeah, they look at statistics of spacings between adjacent levels of billiards, and then they find, well, I will come to that. They find universal aspects of statistics of billiards, right? I mean, of course, again, most of you have seen that, but you know, this is Coloquio. Maybe some have not. So I'm still giving this, but yeah, but then you see that there is, I mean, there's been a lot of research in the 90s, in particular in the context of many-body mesoscopic physics related to billiards and all that. Then again, I mentioned my old friend Giulio. With him, we were responsible for another kind of experiment, numerical experiment on billiards, which also connected chaos to classical chaos, let's say, to quantum mechanics, namely. You can play a Young experiment, interference experiment, right? But you do it in a way that you close a wave packet in a resonator, right? I mean, usually you would just shine a wave packet from some direction, right, in infinite space, and then you would look at what happens at the screen. But with Julia, what we did, we proposed to look at a wave packet inside the billiards, and then depending on the shape of the billiard, you can get either interference fringe or something which dephases. Yeah, that's just. I mean, what I want to say here is just that there were many ways of characterizing quantum chaos in semi-classical systems. Even maybe one can even find even more ways to characterize chaos in systems without a classical limit, as you will hear later. Yeah. So I mean, there's very little consensus on what quantum chaos is, and maybe even after my talk, you will not have any better definition of quantum chaos, but still. Yeah, it's an interesting subject. So now let me start with a more serious slide. So again, those who attend the conference this week have seen versions of this slide before in various talks, but I still repeat it. So that's basically what we are all about. What we are all thinking about, right? I mean, it's about quantum chaos conjecture, right? I prefer not to call it Bohiga's conjecture, even though it's known as Bohiga's conjecture, but since, as was mentioned the other day, it was actually first kind of dreamed of by our friend Julio again, with collaborators in 4 years before, right? So I think it's more fair to just call it quantum chaos conjecture. And well, as you know, I mean, conjecture proposes that there should be universality in spectral statistics of quantized systems, which in classical limit they are chaotic. And there is the reverse quantum chaos conjecture, the so-called Berry-Tabor conjecture, which says that what happens in the opposite case, when the classical limit is completely integrable, then there is a kind of heuristic argument which explains why spectrum should have Poisson statistics. And yeah, and what is the goal of my talk, and what is the goal of the research in our group for the last few years, is to establish mechanisms why quantum chaos conjecture should be true, or maybe under some very restricted kind of context, maybe even prove some aspects of it for many-body quantum systems without classical limit. So now, I mean, as you know, I mean, in quantum, let's say, particularly in the new topical field of quantum computing, people are interested in systems of quantum qubits, which are spin-1/2 particles, right? Represented as whatever, I mean, Josephson currents or photons or whatever, that simple quantum degrees of freedom, which have h bar equal to 1. Still, we expect that in the thermodynamic limit of many qubits in the regime of quantum chaos, which was discussed today by Alex in the conference, these models are expected to behave as random matrix theory. So the question is why? I mean, that's my question. So, I mean, I'll try to give you some heuristics of why this should be true. Why should systems without classical limit? But first, we have to understand why maybe we should expect it to be true for systems with classical limit. So, but let's start with something very simple. Let's start with a simple kind of order parameter, which will be characterizing quantum chaos for us. The simplest possible measure of correlations, of spectral correlations, and that's the so-called spectral form factor. So I'm just giving a couple of formulas here. I'm sorry, again, I try to be as non-technical as possible, but this is just something that, I mean, one can derive in 5 minutes on 2 lines, you know, just starting from a spectrum. So what we are interested in now are spectra of many-body, well, mostly many-body dynamical quantum dynamical systems, many-body spin systems, if you want. And moreover, I will be interested in Floquet systems, so systems which are periodically driven. And why is that? I mean, again, maybe you've heard, I mean, those of you who have ever tried to compute any spectral statistics know about problems with spectral unfolding and spectral edges and all that. So these models, which are periodically driven in time, don't have this, they don't suffer from this problem because the spectrum is just defined with respect to mod 2 pi. Basically, the spectrum is now called quasi-energy spectrum. The eigenfaces of the unitary operator are points between 0 and 2 pi, mod 2 pi. So there are points on a circle, so there is no edge. And if the system is kind of sufficiently strongly coupled, there's no reason to believe that one quasi-energy would be preferred with respect to any other. So basically the natural kind of assumption is that the spectral density should be on average flat. And then what you define as a next kind of thing that to analyze is a pair correlation function. So assuming that this guy is on average flat, now you compute the two-point correlation function of the spectral density is defined as a train of deltas. You define rho centered around pi, displaced by theta, and then you average over phi. So this is what you can define for each individual spectrum, and this you call R of phi, which is a two-point function. And then you can compute the Fourier transform of the two-point function. Again, it's a two-line calculation. What you get is basically a simple expression in terms of a double sum over eigenphases, right? With the exponent e to the it times the difference of two eigenphases, right? Now this t is integer, right? Because we are doing now a Fourier analysis on a circle. So the Fourier variable is an integer, and that makes sense because we have a Floquet dynamics where time is an integer period of a number of revolutions of a Floquet drive. So now remember, t for me is always an integer, and this is a spectral form factor, which is just this double sum over over the phases multiplied by a difference of phases multiplied by time t. And this you can just in turn write as a trace, because this is just each sum is a trace, and these are two independent sums. One is conjugate, complex conjugate with respect to another. So this is trace of t, trace of u to the t modulus square. And then if one is picky, one has to subtract the delta function at t equal to 0. And I also apologize to my expert colleagues for using a non-conventional normalization for the spectral form factor. So I normalize it in a way that I don't have any prefactor around here. So basically this would not, usually people normalize it by 1 over n squared here, so that it doesn't have a divergence at time equal to 0, but I normalize it in a different way, but it doesn't really matter. It's just that you should be careful when you read my plots, that normalization is maybe a little bit non-standard. Now, what one has to stress here is this is a very nice measure. It's a kind of minimal measure of spectral correlations, but the fact it's being more minimal and most crisp to features of chaos, it means that it's also very sensitive to numerical, well, not only numerical. I mean, it's statistically not the best thing to analyze because it's not self-averaging, right? So I mean, if you compute it for an individual dynamical system, it doesn't make sense. You have to average over an ensemble of nearby, if you want, nearby dynamical systems. You can also average over moving. You can also do moving time average, but you have to use some sort of expectation value with respect to some ensembles. Okay, so then you can just, you have seen versions of this picture in the conference before during this week, but I'm now just reiterating this figure in a way that it just stresses the main part, the essential part, which is the ramp, the so-called spectral ramp, of the spectral form factor. So now if we look at the dynamics of spectral form factor for the various times, you see that with respect to different, this is what happens for random matrix theory. So for different random matrix ensembles from orthogonal through unitary to symplectic, you see that this grows with different slope. This goes with slope 1 for unitary, with slope 2 for orthogonal, and 1/2 for symplectic. And then something happens at the critical time scale, which is the Heisenberg time, which has to do with the mean level spacing. So when the time is of the order of mean level spacing, then all of these phase differences become order 2 pi. So because they become essentially pseudo-random numbers, so there could be no constructive interference anymore. Well, there could be no growth anymore. So what you get is basically a plateau, right? You can get, at most, these are n square random phases. So you can grow it to most n, and that is what you get. You can compute that, you get n. Okay, so this is something very simple, but you can compute that. People have, there are textbook monographs in random matrix theory which contain these results. So the main question of, let's say, quantum chaos is to establish why on Earth simple dynamical systems should follow random matrix theory. Because for simple dynamical systems, even many body, the Hamiltonians or the Floquet operators are highly non-random. So first of all, they're non-random, but not only that, they have Hamiltonians have only few matrix elements in each row, but random matrices have of the exponentially many matrix elements in each row, right? In terms of number of particles. So yeah. So now, okay, so then one more important thing to stress here is this short time scale. There is a long time scale. There are two time scales which one has to stress. There is a long time scale, which is the Heisenberg time, but there is a short time scale, which is what people refer to, in the quantum chaos community, let's say in semi-classical chaos, this should be referred to as Ehrenfest time, because it's related to validity of Ehrenfest theorem. So when you start with a wave packet, there is a finite time proportional to log h bar in chaotic systems, after which wave packet dynamics no longer make sense. And then this is only after that time random matrices can start to apply. But in disordered metals, this can have a different origin, and it's referred to as a Tauless time. It can be, so for example, for systems with conserved quantities, this can be related to diffusion. So these times can grow with the system size, but for example, like L square, but still is much shorter than the Hilbert space dimension, which is n, which is like 2 to the L for me. So my notation will be curly n will be Hilbert space dimension, and L will be number of particles, which for qubits will be typically, n will be 2 to the L. And right, so now I mentioned there was this main result. I would say this was probably the main kind of success of quantum chaos of single particle physics, if you want, or semi-classical quantum chaos, which was sort of the heuristic proof of quantum chaos conjecture. And I think one of the authors of this kind of result is here, Alex Altland. This was done essentially around a group of Itzhake, 2004. But it all started from the very first one of the first ideas in this field, which was due to Michael Berry, who explained already the first order of this semi-classical expansion. So the idea is, okay, can we derive random matrix spectral form factor from semi-classics systematically, so order by order, perturbatively. So the first order, linear order in time, so just the spectral ramp, this seems to be easy, right? I mean, you just use I'm assuming now, again, I have a Floquet dynamic, so I'm just using, if you want, Gutzwiller trace formula or a Feynman path integral representation of the propagator, right? You do the trace of u to the t, you get a sum over all stationary points, but these stationary points are just periodic orbits which come back exactly after period time t, because there's trace of u to the t. Then you have a double sum, right? You have two traces, you have double sum, you have two periodic orbits, you have sum over two periodic orbits, and then Michael Berry suggested that this can only have contribution when the two actions of the two orbits are the same. So when there is a constructive interference in this orbit difference. And this can happen, of course, if there is no reason for accidental degeneracies of the classical actions. This can only happen if the two orbits are exactly the same. And then you get the sum over the Jacobian prefactors, right, modulo squared. And there is a kind of a sum rule, which is simply a statement of classical ergodicity, so-called Osorio de Almeida Hanai sum rule, which explains you why this should be just equal to the time duration of the orbit, right? So this should be just equal to the t, unless you have time reversal symmetry. If you have time reversal symmetry, then you pair not orbit only with itself, but you pair it with its time reversed partner, then you have to. And this argument, this was the simple argument, but actually, the rest of the work, which took people like, there was 16 years to the second order term by Martin Sieber and Klaus Richter, and then there was another few years until the final kind of diagrammatics had been developed by the group of Hake. So you see, there was a long time that people have really worked out all the details, but the idea was kind of in the air. Okay, but that's sort of right. But if you want, what is really the origin of this time t, of this prefactor t here? I mean, the linear ramp. You should imagine this is, as you will see, this is something that should be related to time translation invariance. Okay, but yeah, this is the result that has been around now for a while, like 20 years, and it's a very nice result. But the question is why people actually in condensed matter physics, why actually they use quantum chaos conjecture also for systems which have nothing to do with classical limit. Like if you look at some review papers in this field, like this is from the review paper by Lea Santos and Marcos Rigol, you find figures like this. So you have models like this, right, which some people find familiar. It's a free form. I mean, it's a fermionic model in 1D with nearest neighbor hopping, nearest neighbor tunneling, next to nearest neighbor tunneling, plus nearest neighbor and next to nearest neighbor interaction. So we put next to nearest neighbor terms in order to break integrability, because with J prime, V prime equal to 0, this model is just integrable, is equivalent to integrable Heisenberg XLZ spin chain. So the spectral like level spacing distribution is Poisson. But when you increase these primed parameters, like to a small value, I think here they go up to, even for a very small value, you start to approach, for example, 0.08, you start to approach very well the Wigner-Dyson, right? And then, this is this, this was before the people started to analyze spectral spacing ratios, but anyway, you get this standard transition from Poisson to Wigner-Dyson. And the question is why? I mean, there is no classical limit. This model is non-integrable, but why should you expect non-integrable systems to follow random matrices? Because, as I said, there are only few matrix elements of these Hamiltonians in each row, so it's highly sparse matrix. I mean, then you power it, but still, Okay, so now it's kind of remarkable. I mean, this is, one of these coincidences in physics, right? Where different fields arrive to similar problems at the same time, right? Without even talking to themselves, right? Like, for example, there was a interest developed around quantum chaos, let's say spectral quantum chaos, because I should probably give you a disclaimer. I will not talk about autox and quantum chaos around that, right? Which was basically stimulated by Kitaya, people around him. I will not talk about autox. I will only talk about spectral quantum chaos. But even though spectral quantum chaos has also been kind of proposed. These problems have also been proposed kind of independently, more or less in the field of high energy physics. People around Schenker and Stanford. And yeah, you see these people have analyzed spin chains, and they have or SYK model as a model of black hole, and yeah, they argue that this, since this is a model which follows random matrix statistics, it should be considered as a quantum chaotic system. Yeah, there are then different arguments explaining why it should be actually the most chaotic quantum system in the given context. But okay, I mean, this is another field. I'm not going to enter it, but I'm just giving you as a kind of interesting reference. So this was around 2017, 2018, and yeah, and then there was a papers which came from our group, and independently. This was really independent, but also from the same kind of perspective from the group of John Chocker in Oxford, trying to understand why systems with local interactions develop random matrix statistics. So, I mean, there is, I will give you a short kind of summary of the first paper, which we did in 2018 with PhD students at the time in our group, which give a kind of very crude, heuristic idea why should you expect random matrix statistics in spin 1/2 chains, while this paper by Chocker and friends explains why one gets random matrix statistics in local interacting systems of Q dits in the limit of D, or what they call Q, which is local Hilbert space dimension going to infinities. So this is not really what I want. I mean, I would say honestly, this is really not what I want, because they still need some sort of large Q limit. I mean, this is still a kind of perturbative in that sense, or asymptotic calculation in that sense, that it's only true in the large Q limit. So in Q, you can imagine as a kind of Planck constant. But anyway, so as you will see, there is one has to trade different sort of assumptions, right? I mean, either you take large local Hilbert space dimension, or you take, as we did, as you will see in the next slide, or you take some slightly non-local interactions. So what we do here, I mean, this is just I will not guide you through the details of this calculation, but this is just one slide summary of the main result of this paper. The idea is, again, is basically this model kind of it's like a random phase model, if you want. We call it a random phase model, and it's a bit similar to random energy model that people discuss in glass physics, in spin glass physics. So it's like a Floquet version of random energy model, if you want. So you take two Hamiltonians, but in order to make it less random, you can imagine that H0 is not fully random Ising model, but it's a model which is dominantly given by the first order and second order terms. So order which is linear, a simple sum over spins with some fields, and sum of interactions with some two particle interaction. And then you can think of high order terms in order to justify the random model. But what we did here was we really looked at just this Ising model, right? This is and we use this random phase model as a comparison. So we take a random Ising model with this unperturbed classical Ising chain, if you want, and this two particle interaction will be some sort of power law decaying with the distance. So it might be just kind of random, but it turns out that all the conclusions are still true if this is sufficiently slowly decaying, but also sufficiently rapidly decaying. I will not go into that, but there is some sort of power law which is between power 1 and power 2, which is kind of non-mean field on one hand, and also not local interactions, which are harder, for which these conclusions could be true. And then one can compute the spectral form factor kind of with some assumptions, let's say, which I will not go through, but one can compute spectral form factor, or let's say analytically, perturbatively, and one can find a result which is actually giving you the linear ramp. But what is remarkable, you can also get the Sieber-Richter term. So you can get the first two terms. What we did was we actually computed the first two terms of the semi-classical expansion. This is, of course, it's not a rigorous result. I mean, there are some assumptions, there are these random phase assumptions and all that. But there is a nice kind of numerics corroborating this assumption. I mean, proving these assumptions. So, I mean, one is the random phase model, and the other is this is a semi-log scale, so it's a bit strange. This is a linear ramp, and one is the random phase model, and the other is numerics. I mean, this was just a warm up, let's say. I mean, warm-up of what I wanted to discuss. And the rest of my talk will be around a class of models, which we have kind of found out later. And this was the work which I should mainly, thank my collaborators, Bruno Bertini and Pavel Kos, who were postdoc and a PhD student in my group at the time. And these models are actually really models of brickwork quantum circuits, so kind of generic models of quantum computation, something that actually people with quantum simulators actually can do, and they have done, and they can implement. But it is a particular class of quantum circuits with a gate which satisfies particular kind of nice condition, which we call dual-unitarity. So now imagine you have a gate, and the gate is like a unitary operation which acts on two states. I call them I and J of two qubits or qubits, and spits out two states K and L. You can also think of it as an S matrix. In a high energy context, this could be like an S matrix, but in a condensed matter context, it's like a gate. And this has a property which says that this should be unitary if you look at it either this way or that way. So it should be unitary under reshuffling of the basis. So we can define a unitary matrix which maps I states IK into states J and L, and we define this matrix as U tilde. So we define this reshuffling operation, U to U tilde. And then we call a gate dual unitary if both U and U tilde are unitary. Of course, U is unitary by assumption, but U tilde being unitary is a kind of a special condition. You may think it's a very fine-tuned, very special condition, but it's not so much so fine-tuned as I will. Probably I will not discuss details, but you just have to fix 2 out of 16 parameters, for example, for qubits, in order to make it dual unitary. So it's a codimension 2 manifold in the unitary group. Okay, and then you can make circuits out of this. So you can just this is like a Lego, and now you make walls out of Lego bricks, right? And the wall with height 4 is like a circuit of 2 time steps, of 2 Floquet time steps. Now this is a Floquet evolution with 2 half time steps because they are shifted by one side mutually. So this is the full time step. So these are 2 full time steps. And this, for example, this could be translation invariant, maybe not. These gates could be all the same, could be different. It doesn't really matter. But this is just an example of a circuit with 2 time steps and L fundamental cells. So there are 12 qubits with period 6. Right. So now this is the way you could maybe define these circuits. You can define it as a product of the even and the odd layer of gates. One layer is just a tensor product of L fundamental gates, and the other is just shifted by this shift operator. This pi denotes a shift operator on one side of a string of qubits of size L to L. So just to make sure that we are that we have an even number of qubits, I denote by L the half number of qubits. Okay, now you can define a dual circuit. You can define a circuit in this direction. And for that, you could just use a dual gate. And then this means that you have a system of size 4, or L equal 2, for time of duration 6, right? Now this is a space-time or dual time. But still, the circuit itself is unitary. So you can just, as you can think of it as a dynamics, right? As a unitary dynamics. Yeah. And right. And then clearly you have a kind of, if you want to compute a trace of U to the T, right? This is like a partition sum, because trace meaning, well, for example, you compute, you assume periodic boundary conditions, right? You can identify these wires here, but you can do the trace, and trace means you identify these vertical periodic boundaries. So in trace of U to the T would be like trace of U to the T would be like trace of U tilde to the L, right? So it's like a duality of traces, and this is just like computing partition sum using row or column transform matrix. These are just a row or column transform matrices of some sort of complexified partition sum. And that's the idea. The idea now is to approach interesting questions in physics from the perspective of statistical mechanics, forgetting that weights should be positive, forgetting that the weights should be positive in statistical mechanics, but just use the algebraic tools of statistical mechanics to try to evaluate these objects. Okay. So for example, what happens now? I try to reduce number of formulas to a minimum, but then I'll give you pictures, right? I'm sorry, these pictures still look scary, I understand. But you should just imagine that these actual pictures are very useful because they allow us to do calculations. I mean, this is just a way of how we would then prove quantum chaos conjecture. Well, how we would prove linear ramp of spectral form factor for a dual unitary circuit. So imagine now you have a dual unitary circuit. You may have a one layer of Floquet dynamics, which I call U sub L now, because the stress, the size dependence. And then what I will do now, I will take magnetic, so I'll take 2 qubit gates, which are all the same. So these are the light red and dark red, so that just to stress that this could be 2 different gates. But then I take a single qubit gates, these are these circles, which are in different shades of blue. Different shades of blue means that there are different magnetic fields here, which kind of mimic disorder, right? I mean, I need disorder for 2 reasons. One reason being that I need to average over disorder, so in order to make the problem self-averaging. The second reason is that I need to break translation invariance. But that disorder is still rather innocent because I will be able to switch off the disorder at the end of calculation. But the limit, disorder going to 0 and thermodynamic limit, they are not commuting. So it's important that I keep small disorder until I do thermodynamic limit, and only then switch it off to 0. So yeah, then there's another caveat, I mean, another kind of disclaimer I have to make. I'm only making statement about thermodynamic limit, which is quite restrictive, as we can understand after a thought. But still, it's, I think, a nice result. But yeah, so, okay, so then, well, I mean, the reason why we were excited, and I'm excited still about this type of calculation, is that we can map the calculation of spectral form factor to a nice algebraic problem, which is maybe interesting even from the point of view of mathematics, as you will see in the next slide. But again, I will not be able to go into details. It's just like a kind of flash. But still, I mean, first step is to rewrite the calculation of spectral form factor as a transfer matrix, in terms of a transfer matrix. But now, spectral form factor, which is the simplest object of spectral statistics, is a 2-replica object. I need 2 traces. This is trace of u to the t. This is trace of u to the t star. So now imagine this was my partition sum from before. But now this partition sum includes these little bullets here, which are these single qubit gates, which are there in order to provide mechanism of averaging. They are different. They are system. This is time, right? This time layer, this is space. So these guys are different. I'm sorry, this colors is not so good, but these are different in different points in space, but they are the same at the same instance of time. Now time has period 2, so this guy is the same as this, is the same as this. And this time is exactly the same as this, and this guy is exactly the same as this. So this repeats periodically with period 2 in the time direction because it's Floquet, but it has disorder in the space direction. Now, what I will do, I will use my duality. I will use my space-time duality to change. I mean, now, normally we would just apply dynamics in time direction, right? You just iterate Floquet operator on the state, or then take the trace, average over all states. But now we propose to do the opposite, to iterate this in the space direction. So to cut out a vertical tower. Oh, sorry, I erased that slide. I should have kept it because I wanted to explain it, but sorry for that. So what I did now is just the fact that the disorder is IID. So which means that I can take its expectation value, or these two products of 2 replicas, as a product of expectation values of each tower, each column separately. So that each column separately is like and then I can do disorder averaging, because now this is IID, so I can do disorder averaging independently, and so on and so forth. So I can basically take a power of a transfer matrix. This becomes a transfer matrix, which I can take trace to power L. Okay, so now this calculation is synthesized here. I mean, is extracted here in this one line. Of course, it's a very heavy line, but it's just an abstract algebra, nothing else. It's an elementary algebra. So it's just just the way how you can write this thing, in terms of u tilde, right? Rather than you can write it in terms of u tilde. You just assume that the trace of the tensor product is the product of the traces, or vice versa, and then you get at the end of the day, this disorder average now can be done step by step. So everything is just trace of t to the power L. Now the rest of the game is to show some nice spectral properties of this transfer matrix. Now this transfer matrix is really nice because it's a quantum channel, because now it's a composition of a unitary. Now the dual dynamics is also unitary, and that's why we want dual unitarity. This dynamics is unitary, and then there's the expectation value with respect to the local field, right? So it's like this representation of quantum channels, which it's an average over unitary quantum channels. You can write a certain class of quantum channels as average over unitaries, and this is quantum channel like that. Okay, so fine. And now right, and now what we can show is that the spectrum of this transfer matrix has an eigenvalue 1 with degeneracy T, and that there is a gap with respect to the rest of the spectrum. And that means in the thermodynamic limit, this trace of T to the L should go to T, and that's the linear length. And that comes as a consequence of time translation invariance, as you will see if you look at the statement of this theorem. So this is basically the main result that we have formulated with Bruno and Pavel, which is restatement of the problem in terms of algebraic problem. And that algebraic problem is connected to finding the eigenspace of eigenvalue 1 of this transfer matrix. So the eigenspace, this operator is basically a quantum channel, so it acts on a space of operators, a space of physical observables. And you can characterize its eigenspace of eigenvalue 1 in terms of what mathematicians call commutant. So a set of all operators which simultaneously commute with magnetization and interaction. All components of magnetization, which are spelled out here, and all components of interaction. All these are translation invariant operators in time. So now the time is the new space, right? The size of my transfer matrix is the time, duration time. And these are translation invariant in time. So I can immediately find a possible candidate set for which spans the commutant, which is the set of T possible translation operators. This is translation invariant in time. So all the translation operators commute with magnetization and its interaction and spin interactions, which are translation invariant. So the rest of the proof is to show that there's no other elements in the commutant. So commutant, that the linear span of commutant has a dimension which is not larger than T. So there is no linearly independent operator which also commutes with these guys. And that's basically an exercise in the representation theory. Okay, that's basically the and then of course this is 20 pages of the proof, but the idea is very simple. Okay, now yeah, is there any question maybe for this part? No, I mean, I'm sorry, still I had to be a bit little technical, but yeah. 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 No, not that I can think, not that I can imagine. I mean, this is really, this is kind of unpleasant, right? Because we don't have really heuristic idea why this works nicely. I can have some resemblance to periodic orbit theory in our first paper. In our first paper, actually, we have some sort of path into kind of a stochastic path integral of trace of U to the T in terms of classical computational states or quantum computational states basis, and then you can think of these loops as periodic orbits that I've shown there. But here, for local interactions are harder. And no. Thanks for the question. Okay, now, yeah, so I will not, I mean, I try to keep my time and your patience to a reasonable level. So let me just close with a couple of other stuff that we or people can do with this class of models. There has been an interesting series of papers by Wei Ho and Choi, Matteo Puliti, also on constructing what people call exact projected ensembles related to the concept known as deep thermalization. So, I mean, people discuss issues of thermalization as a relaxation of initial state to a thermal state. You can also think of generalizing this concept, looking at not only average values, but also fluctuations of physical observables. For that, you have to compute density matrix on a tensor product of several replicas of your physical space. And it turns out that dual unitary circuits are also very suitable for providing exact results on that. So it turns out that actually dual unitaries provide, I mean, very nice toy models. And now I try to go back to my first slide, like cat maps of many-body physics, which one can use to learn about not only quantum chaos, but also about thermalization in general, like deep thermalization. And second kind of result, which I enjoyed very much, I have no idea how important it would be. It's definitely extremely amusing. In particular here, I would like to raise attention of people who have affinity to high energy physics to maybe give me an opinion about this work if they know. If they don't, please take a look. I mean, Luis Massanes, who is a rather famous person in quantum information theory and fundamental questions of quantum mechanics, he came up with this kind of nice construction of discrete holography or discrete CFTs in terms of dual unitaries, which have additional symmetries. So he imposed additional symmetry on dual unitaries, and then he found basically, I mean, relativistic QFT, holography, black holes, everything. I mean, it's kind of amusing at least. And then, of course, as I mentioned already, I mean, dual unitaries have been used already in quantum simulations. For example, in the Honeywell platform, they have used it as a nice kind of illustration for their experiment. I forgot to say, and I on purpose skipped this kind of discussion, but dual unitaries, among other things, have also very simple and nice behavior of dynamical correlation functions. And this is again one thing which you might be interested most about some physical many-body model, right? What are its dynamical correlations, right? And this model is 1D, or it's extended, so you can think of what are the correlations between observable here and now and another observable there later. And it turns out that there are non-trivial correlations only when this now and later are connected by a light ray. So with something that has 1 or -1. So that has to do with the fact that dual unitary circuits have causalities in space and time. So the intersection of causalities in space and time is only something that travels with speed of light. So that gives us a very nice, very simple characterization of dynamical correlations. And my last part will be related to my future vision. I mean, not only that, I mean, there is a paper actually, which maybe I can advocate here, but this is like paper is about, let's say, not this one, but this one. This paper is about more or less a half result, even though we were quite excited about it, so we still publish it, but you know, it's like a first step in this direction. But the direction is really to treat dual unitaries as a kind of unperturbed models, and now systematically build perturbation theory on top of it. So to write some sort of path integral expansion of perturbed space-time correlators of perturbed dual unitaries. So that was the point of this work, but you can ask this question more in general. So for example, I mean, this is just a setup that one can consider. One can consider dynamical correlation functions of observable A with observable B. Now I did one thing which I haven't yet explained. I folded the circuit because this is now something that has a forward and backward component, right? I mean, look at dynamical correlations, but you know, you should use propagator backward and forward in time. You should do the so-called Keldysh contour, but you can do also a trick and just fold things and just treat like a uniform dynamics in double Hilbert space in forward direction. And this is the same equivalent to saying that you have a double Hilbert space, like for qubits dimension 4, which propagates directly operators, right? So this is like a tensor product of the gate with itself, its transpose. And then unitarity can be expressed simply by attaching these lines together, which means like contracting with a little circle, and this is unitarity. And dual unitarity means just like attaching little circles, which means contracting the wires sideways, and then you get these kind of contractions. So these simple contractions of these diagrams basically can be used then to simplify circuits, right? To simplify correlation functions. So now I'm just, for the rest of my talk, which is just 2 more slides, so please bear with me, but for the rest of my talk, I will just kind of show you how to simplify simple diagrams of correlation functions using these rules, right? I mean, unitarity just means you simplify things vertically, and then it means that even if you start from something that has rectangular geometry, using these rules, you can contract it to this kind of diamond geometry, right? This kind of skewed rectangle. That means you can cut away everything that's outside of the causal cone, the forward causal cone, I mean the temporal causal cone. But now if the gate is dual unitary, and for dual unitaries, I will use the yellow code. For dual unitaries, you can also contract sideways. And if you contract sideways, you will contract things to 0, because the observables, by definition, by assumption, will be traceless. So being traceless means that if you contract observable with an empty circle, it's like taking the trace, meaning being 0. So which means that this can only be non-zero if these 2 guys lie on the same line. So if you place A on the same light ray as B, and then you get a transfer, then you have a correlation function, which has this form, which is just like a 1D transfer matrix. This is like a 1D zinc model, if you want. It's a transfer matrix of a 1D spin chain, right? Or not a spin chain, but I mean, really 1D model, one qubit. It's a quantum channel. These beasts now are just quantum channels of a single qubit, and the correlation function is just iteration of a quantum channel. Okay, I mean, and now, but the rest of this game is now to analyze things which are much more interesting, to analyze things which are like correlation functions where you place a gate which is non-dual unitary once in a while. So you take dual unitary gates most of the time, but then sometimes you make a mistake. And then you play, let's take an impurity, right? You take an impurity gate, which is not exactly the dual unitary. Then what you have shown in this paper, that under some conditions, which I've got no time to discuss, but there are some interesting kind of maybe phase transition, maybe crossover, but there's some transition in terms of parameters of the gate. And if you're in the right part of the parameter space, you can show more or less analytically, or in some restricted concept, in some restricted context of random circuits, you can, well, partly random circuits, you can prove it, but otherwise it's a more or less, again, heuristic argument, showing that this can be just given as a sum over paths, right? Sum over scattering paths from initial operator to final operator, scattered being piecewise linear, piecewise straight, and scattered being turning at the impurity gates. And this is like a 1D path integral. It's like a 1D path integral in discrete space-time, if you want. So it's a much simpler problem. It's a one-particle problem. So once you have this property, you can compute many body correlation functions, like a 1D path integrals. And you can compute, for example, what happens to a correlation function under small perturbation. Now, this is an example, numerical example. You take an observable, and this is X is a displacement with respect to another observable. So if there is no perturbation, then the only non-zero correlation is along light ray, which means here. But now if you take some finite perturbation, then you get non-trivial correlations also within the causal cone, which otherwise within the forward causal cone, temporal causal cone, which for dual unitaries was prohibited, which was 0. And we have an explicit formula, which is a simple one-particle formula for the correlation in this causal cone. Okay, so now I think I will just skip that. I mean, this is just, it was already discussed maybe in the last talk of the lecture, or of the conference. So I will skip that point. Yeah, so I will just close my talk with maybe giving you my vision, what should one do next. Yes, you might think you might like this kind of model. Maybe you can even hate it because it's so fine-tuned and so strange, right? I mean, physics is not very generic. This should be good. We should agree on. One other thing which I forgot to stress is that, for example, if you look at spectral form factor, for dual unitaries, we found that the spectral form factor is just T. And we took thermodynamic limit on the way, which means we push Heisenberg time to infinity. And spectral form factor just grows as T. So where is the Thouless time? Where is the Ehrenfest time? Well, H bar is not small, so there is no Ehrenfest time. But why there is no Thouless time? Why there is no short time scale? I mean, if you look at papers of John Choker's group, I mean, they always find some time scale, which is typically scaling as a logarithm of system size, but still it's a short time scale which grows with the system, which with the number of particles, where random matrix theory does not yet work. And then there are some some interesting transient effects. Now, in our case of dual unitary circuits, there is no Thouless time. Everything works. Random matrix theory works from time 0 onwards. So these models are actually also interesting, maybe from this direction, from this perspective, that they look like critical chaotic systems. Critical in the sense there's no time scale, there's no scale. They are basically chaotic on all scales in thermodynamics. Now, what would be the interesting questions? Well, apart from the one which I already discussed briefly in the last slide, which is the diagrammatic perturbation theory around chaotic dual unitary models, which would, yeah, I think the main question would be then kind of potential proof of stability of ergodic many-body phases. As you've heard also in some talks briefly in the conference, I mean, there was a lot of debate around stability of many-body localized phase, which is still not settled. And I personally believe it's a very hard question, which will be hard to settle in the short-term future. But I think there is a much easier question, which is already kind of very interesting, which is a question about stability of many-body ergodic phase. We probably would, first of all, we should all agree that ergodic phases should be stable under perturbations, right? It's a very reasonable thing to expect. You may say, okay, why would you bother proving something that's obvious? Yeah, but I think it's still interesting because then you could maybe provide bounds on how much you can perturb some exactly controllable ergodic system like dual unitary circuits to still have exactly ergodic, I mean, rigorously ergodic. So one, I think, one kind of line of research which would follow from here, I think it would be like proving that. And another kind of hard question, which I have no idea how to tackle, But I think it's also very interesting, and it has to do with the ideas of eigenstate thermalization. I mean, as you know, there is also, I mean, people who follow the field, they know that there is this extremely topical and interesting result, which is not really a result, but it's conjecture corroborated by vast amount of numerics, but it's still just a conjecture, arguing that quantum many-body chaotic systems should have eigenstates which are random. So one can apply that, and then one can derive some simple statements about statistics of matrix elements. And I think it would be great to have some models for which this could be rigorously proven. I mean, we know that those of us who grew up in, again, quantum chaos of single particles, we know that even in the 70s and 80s, mathematicians have tried to prove quantum ergodicity for simple models like billiards, single particle problems, constant negative curvature surface motions. That, I mean, I think, and then, you know, in many body physics, I have seen nothing like that. I mean, the question is, can we approach a similar kind of question in many body chaotic systems? I mean, can one provide some results on? Can one provide some models, again, simple minimal models like billiards with you know, K billiards for which this could be provable? Yeah, that would be, I think, great, but I have no idea how to even to start. I mean, I thought for a while, I mean, that dual unitaries could give us some sort of inspiration how to do that, but the problem is that to do anything with dual unitaries, you have to do thermodynamic limit first. And that's, of course, no go for eigenstate thermalization. I mean, for eigenstate thermalization, you have to do time to infinity limit first, because that's how you get eigenstates, right? And you have to resolve the spectrum by doing the large T limit. And only then, because this is finite systems, only then you should scale the system size to infinity and try to argue what happens. So we need another set of kind of methods or models for which one can do the reverse order of limits. I have no idea how. I still hope that dual unitary circuits can teach us something, but yeah, that's a challenge. So with this, I would like to thank you for your attention.
Thank you very much, Tomaž, for this very, very nice talk, very interesting work. Are there comments, questions from the audience? Jack?
I wondered whether you also can calculate 4-point correlations, for example, to see if that also is given by the COE statistics.
It's a very good question. We have a paper on that, which is not a rigorous paper. So there are still holes there. I mean, but I think yes, the answer is yes, but it has not been done because there are still some issues with respect to. I think they are just technical issues, because even the proof for the 2-point function was for the average value of the spectral form factor was quite hard. The proof for the fluctuation. We have it in the archive version of the CMP paper. The referees wanted to took us out because the CMP only publishes results which are proven, right? So they don't want to publish half-baked stuff. But we on purpose kept it in the archive version. So we have a section in the archive version about a result on fluctuations of spectral form factor. Let's say nth moment of the spectral form factor. There's much more difficult combinatorics because then you have to use permutation symmetry between replicas, and then group theory explodes, right? So it's, but if you're interested to look at it,
Okay. Are there further questions?
Tomaž, of course, dual unitaries are fascinating and exactly solvable in many ways. But going back to your, motivation about finding a solvable model, even the cat map is still classical.
Yeah.
Even single particle quantum chaos really doesn't have, I think, a solvable model in the sense that the quantum cat map suffers various kinds of
yes, you're right.
And the quantum bakers is still not solved. So
I know,
in that sense,
yes, but yes, but maybe you can hope in many body limit it gets simpler, right? I mean, because you don't have the H bar. I mean, the H bar is the problem, right? I mean, limit, semi-classical limit is hard. I mean, it's very singular and
Thanks.
very some mathematics.
Okay, further comments?
In the context that we just mentioned, I was thinking a moment before the classical correlation matrices is the Marchenko-Pascal distribution, everything, they have extremely similar properties to the GOE. And so in that sense, I'm wondering whether maybe trick-wise one can get around the H-bar limit by looking at classical behaviors that do some of the things. Now, I was just wondering, I haven't ever thought about it, it came up.
But you talk about Arul's
Yes.
idea, so to look at the single particle quantum map,
Yes.
cat map, so perturbed cat map.
Single particle map now, I mean, what I'm now talking about is always, you know, single particle. Well, it's in many initial conditions if you take it as a random, it is all solved because the correlation is between different sets.
Yes.
But then obviously that, as you know, we tried something to work out with now François Roberto. That was a little high for looking at 3-point correlations in that stuff. There seems to be some interesting things, which I have no idea how they would then correspond.
Mm-hmm.
But
Okay.
obviously, this 3-4 point correlation are of big interest practically.
Yes, and since you ask, I mean, let me reflect on that. Yes, I mean, this also resonates with a, I think, interesting question in terms of dual-unitary dynamics. We had this very simple formula for the 2-point function, but if you look at n-point functions, things get much more complicated, and we don't know how to approach that. I mean, but this could be also interesting. I mean, to look at high point functions of dynamics of dual-unitary circuits. I mean, yeah. So if you look at connected, I mean, we think that connected k-point functions should still be simple, but or zero, or decay much faster than the correlation function itself, the lower point correlation function. But there could be something like a anti-Wick theorem for chaotic dual-unitary circuits, but I mean, just like a fantasy at the moment.
Okay. Are there further
Thomas.
questions?
Thank you. Is there a way to translate this duality to Hamiltonians?
No, that's a good question. Thanks for asking. I mean, the reason is that when you go to Hamiltonian, you have to do the throttle limit, right? And the throttle limit you can only do through, I mean, the gate goes close to identity in the throttle limit. And if you look at the dual of identity, it's a projection. It's a rank 1 projection. So it's as non-unitary as it can be. So it's just that this is physics which is topologically disconnected from Hamiltonian physics. Well, that's also interesting to know.
Okay. Is there any other question? If it's not the case, then thank you again, Thomas. Thank you very much. Okay, and we have now a small reception, I think, here outside. And for those of you who participate in the conference, we will have lunch up the hill at the CIC, just after the reception.